Hello, my name is Alexander Wilcher, and I'll be giving a tutorial on microstrip and stripline design and simulation. This tutorial will use concepts that we previously learned in the class. So today's outline will consist of demonstrating how to design, model, and simulate a microstrip line and a stripline transmission line using the TX line software, Advanced Design System from Keysight, and ANSYS's High Frequency Structure Simulator. To do this, we'll be doing stub matching using a shunt open stub, and this will be designed using a Smith chart initially. We will be matching a 50 ohm transmission line to a 75 plus J40 ohm load. The design stub will then be verified by using ideal components and modeling and simulating it in ADS. After it's verified, we will then use the TX line to design the microstrip line geometries that we'll need to implement in HFSS to simulate this shunt stub. The substrate will be FR4. It will consist of a thickness of 1.57 millimeters. It has a dielectric constant of 4.4 and a dissipation factor of 0.02. We'll be using a copper conductor of 1/2 ounce. After we design this in TX line, of course, we are going to model and simulate this in HFSS. As a bonus for those of you who make it to the end, a 50 ohm strip line for 10 gigahertz will be designed by TX line and then modeled and simulated using HFSS. To design our open shunt stub tuning network, we'll be using a Smith chart. I'm going to go over this pretty quickly as we've done this several times in the class already. The first step is to normalize our load impedance and then plot this normalized impedance on the Smith chart. I'm then going to plot the matching condition. I will draw my standing wave ratio circle, and then I will notice that since this is a shunt stub, I'll be working with admittances, and so I will draw a unit admittance circle. I will then identify the intersection points between the standing wave ratio circle and the unit admittance circle. And starting from the origin and moving toward the edge of the Smith chart, I will draw a line through these two intersection points and our load admittance. This is so that I can, starting at the load admittance, move toward these intersection points, toward the generator, and find a distance that will place me at this on the unit admittance circle. Since I have two distances, I can conclude that I'm going to have two solutions. I am now going to identify the admittances at these two intersection points, and I see that I have a susceptance associated with each. To cancel this susceptance, I'm going to draw a line from the origin to the outer edge of the Smith chart and identify the locations that these susceptances are at. Since this is an open circuited shunt stub, I'm going to draw a line from the origin to the open circuit condition. And from the open circuit condition, moving toward the generator, I'm going to find lengths of line that will give me the susceptances that will cancel the susceptances at these intersection points. I have to take care to make sure that I have the right length of line to create the susceptance to cancel the susceptance at a particular intersection point. Then I will achieve a solution that looks something like this. You'll see that for the load impedance, I have 1.27 nanohenries. Please recognize that this is frequency dependent, and the equation to calculate this is right below the inductance value. Now that we've designed our open shunt stub tuning, we're going to model it in ADS. To do this, we're going to go to the dropdown and go to Basic Components. Starting with the inductor, we're going to place that. We are going to place a terminal, and we're going to place an S parameter sweep. Now that we've completed this, we're going to go to our ideal transmission lines. From here, we're going to need a transmission line. We're going to need a transmission line open circuit. Now that we've arranged our components, we're going to search for a ground. And we're going to put a ground to our open circuited shunt. And of course, our inductor. We're going to use the line tool and connect all of our components together. Now that we have all of our components connected, we're going to set up our sweep. We're going to start from 4 gigahertz and we're going to stop at 6 gigahertz. We're then going to adjust our step size. In this case, I'm going to use a 0.1 megahertz steps. And then we have to input our values. We know that the load resistance is 75 ohms, and we also know that the load inductance is 1.27 nanohenries. The frequency of operation is 5 gigahertz, so I'm going to change that on the frequency dependent components. The transmission line is supposed to be 50 ohms. And now our electrical length is going to be calculated from our line lengths that we determined using the Smith chart. In this case, the open circuited shunt stub is 141.48 degrees. And our transmission line is going to be 75.6 degrees. We are then going to copy this circuit and then paste it. And then calculate our line lengths for solution 2. Once this is completed, we are then going to simulate this. If we've done everything correctly, we should have no errors. We should be able to generate a report. We will select our Smith chart and then take our reflection at port 1, which is the first circuit. We will place a marker and then we will move it to 5 gigahertz. As we can see, this is very close to the matching condition. Similarly, we're going to do the same thing for our second circuit. We also see that this is close to matching condition. However, since the first circuit is a better match, we will use this for our subsequent HFSS simulation. So now that we verified the shunt stub design using ideal ADS components, we are now going to design the microstrip lines that will be used to implement this in HFSS. To do this, we'll be using the TX line software, and we will start with by inputting our material parameters. The dielectric constant is 4.4, the loss tension of FR4 is 0.02, and we're going to set copper. You'll see that I made a mistake here. It should be a 7 there, but the effects are negligible. If you don't believe me, attempt this for yourself. We ensure that the impedance is 50, the frequency is set to 5 gigahertz, and we input our first electrical length. We then verify that the thickness and the height are correct for the conductor and the substrate, and it's going to give us a width of the line and a physical length correlating to that electrical length that we input. We're going to have to do this a second time for the distance from the load to the stub, and we're going to record this second length as well. With these values, we can now move to our HFSS simulation. So with these values, I'm going to move on to HFSS. I'm going to add a project, and now I'm going to add an HFSS design model. I am now going to start drawing our model. Starting with the substrate, I'm going to label it as such. I am then going to select the substrate material, which in this case is FR4. I'm going to verify that the relative permittivity and dielectric loss tangent are those as required. And now I'm going to start adding my parameterization. So I'm going to put in 10 millimeters as a placeholder for sub X and sub Y. And I know my substrate height, it should be 1.57 millimeters. At this point, I'm going to position this in the center at a Z height of 0. I'm going to center it in the XY planes and set the height, have its height set at 0. Height position. Now I'm going to start on the ground by copying the substrate. I'm going to set the material as copper. You can see the bulk conductivity right there. I'm going to give it its material appearance. I'm going to set its Z height, and I'm going to create a new variable for the line thickness, which is 17 micrometers, because we're using a 1/2 ounce copper. And I'm going to reposition it so that it doesn't intersect the substrate. Now we should be able to see it. At this point, I'm going to create my line, my microstrip line. To do this, I'm going to change the height to sub Z, or my Z position to sub Z. I'm gonna give it a line X, and this could be either the width or the length. I'm going to choose the length, and I'm going to double that length, and you'll see why here in a little bit. That means line Y is going to be the width of the microstrip line, which is 3.03 millimeters. You can see it's off center, so I'm going to reposition it. You can see that it's hanging over the edges of the substrate. So I'm going to modify the substrate X, and I'm just going to make it the same as line X. And now you can see that they are the same length in the X direction. I'm going to start working on my stub now. And I know that my stub is going to have a different length in the X direction. And so what I'm going to do is I'm going to make a variable for this. And now I'm going to put the stub length in, which should be 12.72 millimeters. I'm going to take a look at it. Oh, it's not centered. So I'm going to center it. And now that it's centered, what I'm going to do is I'm going to rotate this stub 90 degrees. about the z-axis, and I'm going to move it to the edge of my microstrip line. And you can see that my stub is overhanging the substrate, so I'm going to change my substrate width in the y direction. What I'm going to do is I'm going to put a multiplier on the stub length, the stub x. So let's try stub x times 5. That seems like a little bit more than we need. I'm going to try a multiplier of 4. The reason why I'm reducing this is because the more material or the more items that you add, the more simulation time is going to take, since each piece is going to have to be cut up into little tetrahedra and calculated into. So I'm going to unite my stub and my microstrip line and make them one piece. I'm working on making my wave port now. The wave port, you need to remember that the wave port has certain dimensional requirements. If you look in Canvas inside the HFSS folder, specifically the PDF, the PDF labeled HFSS port basics, you can see why I'm making the port size 5 times the line width and 8 times the substrate height. I am now positioning this port. And its Z position is going to be 0. This should be Y, not X. And after I've done so, you can see that the port is properly positioned. I'm now going to go to HFSS solution type. I'm going to select a modal solution type. I'm going to do an auto open region and have a radiation boundary that's automatically created for me. My solution frequency is 5 gigahertz. I'm going to increase the maximum number of passes. I'm going to set the minimum number of passes at 2. Minimum convergence is going to be 2. You can change these parameters to avoid non-convergence or a local minima. We're going to assign it a wave port. We're going to renormalize this to 50 ohms. What this is saying is that what's behind the port is a 50 ohm transmission line. It's setting that port impedance to 50 ohms. At this point, I'm going to create our load impedance. I'm going to copy our wave port since it has a favorable position that we can modify, and we can also modify its size pretty easily. And you can see that now we have it positioned in between, on the other opposite side, in between the just barely touching the bottom of the microstrip line and barely touching the top of the ground. We're going to put a lumped RLC boundary. We're going to set our impedance and our inductance. It's got to be in series because it's in series between the microstrip line and the ground, or our reference. We're going to draw our series line from our microstrip line to the ground. And that should be our model. So we have our load, our wave port, our microstrip, and our stub. We're going to add a sweep, and I'm going to do a relatively small sweep between 4 and 6 gigahertz. I'm going to save the fields at the basis frequencies so that I can view them later if I'd like. I'm going to validate my model. Oh, and I made a mistake. So when I copied the wave port, it copied over an excitation that I need to remove. And that was sitting on my load impedance. Now I'm going to simulate this. I'm going to have to save this. I'm going to name it tutorial. Microstrip, save. And now through the power of video editing, you're not going to have to watch the entire simulation run. You should see normal completion of simulation. Go to results, go to rectangular plot. We're going to plot our S11. And let's see what we got. So after all of that, we're pretty close, right? That's 4.75. What we wanted was 5 gigahertz, but we're not that far away. I leave it to you to either lengthen or shorten the stub to optimize this for 5 gigahertz. If you made it to the end, I'm going to demonstrate on how I would go about modeling a strip line. The parameters I use for the strip line are in the upper right hand corner. And if you'd like to design this, simply use the TX line for these values. I already put in my HFS design. I'm going to create my substrate. The thickness of my substrate is double the 1.57 value. I'm going to use Rogers Duroid this time. We're going to have to edit the material. So you go here, 2.16 instead, and my dielectric tangent loss is 0.001 instead of 0.0009. And that's going to modify my material values. I'm going to refer to this as the substrate. And just like I did with the microstrip line, I'm going to parameterize it in the X, Y, and Z directions. Now that I've done this and I have my placeholders and my correct substrate thickness, I'm going to position it. And unlike the microstrip line, I'm going to center the Z position as well. There's my substrate. And I'm going to start working on my top ground. I'm going to set my material to copper. I now need to correct its thickness. It's going to be 17 micrometers. Since this is top, I'm going to position it at the top, and there's my top ground. Now I'm going to make my bottom ground simply by copying and repositioning it. I'm going to have to negate the line thickness so that it doesn't intersect the substrate. Name this bottom. Now you can see it's not intersecting the substrate, nor is the top one. And now we're going to work on our strip line. This is going to sit in the center. So all I have to do is line center to line Z. And you can see now that it's right in the middle of that sandwich, my line X, I'm going to make this my strip line width of 2.58 millimeters. And my line length, I know that my guided wavelength is 21 millimeters. I got that from the TX line. I'm going to go 1/4 that value. There's a reason I'm doing 1/4. It's the minimum in which you can get an accurate simulation. The question would be why? And I would like you, if you have the time, to think about it and come up with an answer. So now you can see it's in the middle of the substrate, but the substrate is much longer than our line. So we're going to modify the substrate to be the same length in the Y direction as our strip line. I am going to widen the substrate somewhat. Remember, strip lines have fringing fields, so if your substrate is too close to the strip line, you're going to have interesting results. At this point, I'm going to start making my wave ports. I'm just drawing a rectangle. My Z size will be my substrate height, and my X size will be my substrate X. I will then center it in the X and Z position. And for the Y position, I need to have one at each end of the strip line. I think that will do it. I'm going to copy it and place one at the other end of the strip line. I like to color my ports with this bright green. You don't have to do this. I accidentally selected two. I wanted to select one and add a wave port. I only want the first mode. I want this to be 50 ohms. I'm going to do the same thing to the second one. First mode, renormalize, and we're good to go. The PEC is required. Prior, you had to set your own radiation box. It wasn't automated, and PEC backing wasn't a thing. So you had to have the radiation box against your wave port. I'm going to set up my frequency sweep and analysis. This looks good. Save the basis fields. I don't need it for this demonstration. And I'm going to validate. And at this point, I think we're going to analyze it. Now, through the magic of video editing, you don't have to see that. And here we go. So it normally completed. We're going to take a look at the S parameters. And let's put a marker at our 10 gigahertz. As you can see, these are the results. The blue line represents the S S21 or S12, since this is a reciprocal system, values, since it's close to 0 dB, then you can surmise that it's a good transmission line, right? Alternatively, if you look at S11 and S22, which represent the reflection coefficients at port 1 and port 2, we have minus 30 dB. What does that mean? Well, minus 10 means 10%, minus 20 means 1%, and minus 30 means 0.1%. So only 0.1% of the power is being reflected. That's quite good, and this is a well-designed strip line. I wish you luck on your strip line that you're supposed to be designing for your homework. If you have any questions about this lecture or about that homework, please send me an email or ask me after class. Thank you.